Sorry, I'm late, folks. I went over with my stats class. We were having such a nice chat about confidence intervals. And I kind of went, what time is it? It's 1:02. How did that happen? But we're here now. What have you been working on? What can I help you with?
I've been having a hard time with 9.3 where we get the three equation systems.
Yeah, 9.3 was pretty rough.
It's a lot. It can be a lot of organization, and usually, if you get good with that organizing, you're okay. Has it been the problems in the technique in general, or those big word problems? So I guess my question kind of turns into, should we focus on the word problems, or should we focus on first on the process in general? What do you think?
I don't know about Sean, but I'm having a hard time with the process in general.
Okay.
Yeah, it was the entire homework took a while to get through. It wasn't really a specific question.
Okay. Well, then let's grab a random system here and look at this process. Julia, how about you? But yes. Oh, I don't know what's going on with your mic, but yes, I'll take that as a yes. that was all kinds of scratchy. Okay. So as I said, one of the biggest things here tends to be organization. There are technically some options on how you want to go about this. From 9.1, we did have the substitution method or the elimination method. It is possible to do these by substitution, but it is long, arduous, and horrible. So don't do that. Because these are all x to the first, y to the first, z to the first, we have like terms. So that elimination method will work, and that elimination method tends to be nicer. Fair? You'll notice this 9.3 is referred to as a section on systems of linear equations. That linear means the variables are all to the first power. Fair? So this entire section, that elimination method always works. Fair? So we're going to stick with that. And like you did in 9.1, when we use the elimination method, we picked a variable to get rid of. Right? So in all of these, that's your first job. Pick a variable to eliminate. You've got three variables, x, y, and z. So you've got three choices. And it really doesn't matter which one you choose. Sometimes there are choices that make the problem a little bit easier versus a little bit harder, but any of them will work. So if you're ever unsure, I just have no idea which one to pick one at random, doesn't matter. If you see a reason like, ooh, I want to pick y here because they're all multiples of 2, or I want to pick x because it's first and I like things that are first. If you have a reason, great, pick it. If you can't figure out a reason, just pick one at random, doesn't matter, it'll all work. Fair? So for these three variables in this case, is there any variable that somebody wants to get rid of over the others? Sean doesn't have a preference. Hope you have a preference?
I mean, the y's are all multiples of 2s. So,
So
or the-
they're nice.
They seem-
That does kind of stand out too. Frankly, the ones on the z's, since they're all the same, that's probably where I would start. But let's start with the y's. Why not? It should work, right? So pick a variable to eliminate. You picked the y's. Two. Then pick two equations. And eliminate your choice. So we got three equations here. 1, 2, 3. Pick two of them. Any two of them. And yes, I'm going to make you guys do all these pickings. So of those three equations, pick two.
1 and 2.
1 and 2. Julian, John, you both picked 1 and 2. So we're going to pick equation 1 and equation 2, and we are going to use them to get rid of y. There is nothing formal about that notation. It's just going to help me stay organized. Taking equation 1 and 2, and that little squiggly line, the tilde is the logic symbol for not. So I want to use 1 and 2 and not have y. Fair? So if we just added 1 and 2 together, those y's wouldn't disappear, right? But like you did in 9-1, we could multiply by something to make them disappear, right? Which equations would you want to multiply by what to make the y's go away?
Equation 1 by -2.
Okay, so I'm going to denote that, again, just to help myself stay organized. We're going to go -2 times the equation 1. And that's going to add to equation 2. And our y's are going to go away. Cool? Again, this is just me staying organized. There's nothing formal about it, but gosh, I think it's handy. So that's going to give us what? -12x minus 4y plus 2z equals a positive 52. And then we didn't change 2, so that's 1x plus 4y plus 1z equals -19. So if we add those together, we will have an equation in only x and z. Cool. What? -11x plus 3z equals what, 33? That's wrong, tell me. 33, yeah, okay. Great, that's step 2. We picked two equations and we eliminated our variable. Step 3. Pick two other equations. And eliminate your choice. The key here is as soon as you chose to get rid of y, Hope, that means we have to get rid of y in these first 2 steps. Fair? You can't choose y for the first pairing and then x for the second pairing. It's got to be the same variable both times. Fair? But we do need to make a different choice of equations. If we chose equation 1 and 2 again, we just get this same equation again, right? So it does have to be two other equations or a different pairing. Of course, one of the equations has to be in both pairings because we only have three. But it doesn't matter what one or what combination. So we could do 1 and 3, we could do 2 and 3, both would be fine. Fair? So which two do you want to use? You want to use 1 and 3 or 3 and 2?
Two and three sounds good to me.
2 and 3, okay. So again, we're going to take 2 and 3, and we're going to add those together to get rid of y. Now, adding them together won't get rid of y naturally. We've got to do something to make that happen. But hope this is where your kind of, those are all multiples of 2 thing comes in handy. It's the same multiplied by -2, right? Just this time we're multiplying 2 by -2. Okay. And we're going to get a nice -2x minus 8y minus 2z equals 38. Check me on those. And -4x plus 8y minus 1z equals . So what, -6x minus 3z equals 18. Now that gives us 2 new equations. We now have equation 4 and equation 5, right? Now, if you had made different choices, if you chose a different variable or different pairings, your equations 4 and 5 would be different. And that's okay. It would still work out. But notice equations 4 and 5 only have 2 variables now, right? And because we got rid of the same variable both times, again, that's important, they both have the same variables in them. They're both x and z. This now is a 9-1 problem, right? We got 2 variables, 2 equations. So technically, step 4 is, again, pick a variable to eliminate in the resulting equations. That's just a 9-1 question at that point. Even better, because of the choices we made, it happened to work out that our z's are beautiful, right? So I'm not even going to ask you guys which variable you want to get rid of out of fear of you picking x. So let's just do 4 and 5. So 4 and 5, add those together unmodified. And I'm still going to say getting rid of z just to, keep my notation standard. Again, nothing formal about any of this notation. It just helps me stay organized because there's a lot going on in these problems. But 4 is what, -11x plus 3z equals 33, and -6x minus 3z equals 18. So -17x equals what, 51, which means x equals -3. You all, of course, know that 51 divided by 17 is 30, right? 51 is a good number to know, by the way. It's often one of those numbers we throw in to be tricky. 51, isn't that prime? 3 times 17, man, that 3 times 17 gets people, tricks them. So getting to know that 3 17s 51 is handy. So does that mean we're done? Yeah. We got to find z and y, but we can just back this problem up, right? We could either redo 4 and 5 to get rid of the x instead and have z, or just use good old back substitution. And that's the standard back sub to find other variables. We could extend that you do have to do it in the reverse order. So use what you have to find the last one you got rid of, and then use those 2 to find the first one you got rid of. So this 3 is going to go into those to find z. Once you have the x and z, it can go into those to find y. Fair? So -6 times -3 minus 3z equals 18. So that's interesting. 18 minus 3z equals 18. So z had better equal 0. Or -3z has to equal 0, so z has to equal 0. Then again, pick, I just picked this one at random because it was right there and it didn't have any, 11 in it. Who likes 11s, right? And then put it back into either 1, 2, or 3. Doesn't matter which. I'm going to pick the one that's got smaller numbers in it. So how about the x plus 4y plus z equals -19? So our x is supposed to be 3, -3, plus 4y plus 0 is -19. So -3 plus 4y is -19. So 4y is equal to what, -16? So y is equal to -4. So -3, -4, 0. So is there a lot going on in that process? Yes, absolutely. There's a lot going on there. But the nice thing is the process is really the same every time. Every once in a while, you might get thrown off. Like say this first equation didn't have that term in it. So it was just 6x minus c equals -26. Well, I'm missing, you're missing one a term or one variable. Great. That makes this choice easier. If you're missing that y already, then you already have an xz equation. Use the other 2 to get rid of y again, and you that first step happen for you. Fair? It can throw off your logic a little bit. Go, wait a minute, what am I doing here? But they already gave you one with a variable eliminated, so keep that choice going. And thankful. And again, not to keep droning on about it here. There's nothing particular about any of this like notation of how I'm organizing it. It's just over the years how I've kind of started organizing these. But finding some way to organize all this stuff so you can keep track of what you're doing and why you're doing it is certainly important. But it doesn't have to look like this. As long as it is something you can follow what you're doing, it should work fine. Does that help? Do you want to look at one of the word problems, or do you want to try one of those on your own? So do you want to try one like this on your own, or do you want to look at the word problems?
Let's do a word problem.
Okay. So ooh, they even have a mixture problem in there. That's fun. We can even talk a little word problem strategy with it. Now, none of the ones on the homework are too terrible, but if you go look in your book and try to practice some more of these in your book, which I, of course, always recommend, some of these word problems get a little bit big. And, we're supposed to be getting up to 3 equations with 3 variables in them. It's going to be a lot of information, right? So kind of organizing what you're doing is going to be important. A lot of this section is about, being nice and organized. One of the things I recommend whenever you do a word problem is actually illustrated by what they do here when they ask you a question. Oftentimes, if this was given on a test or textbook homework, all you'd see is this question, right? How many liters of each solution would there be? And the problem would stop. One of the things I've always recommended, or not always, but for at least 5 or 6 years, recommended people do when they're faced with a word problem that's a lot for them is to do exactly what this problem does, is write out your answer with the blanks for what we don't know. Fair? So if we're asked how many liters of each solution should be used, we should use this much of solution, we should use blank of solution 1. We should use blank solution 2. We should use blank solution 3. And the act of writing that out can be surprisingly helpful, because it's really common for people to read big word problems and they'll go through them, they'll write a bunch of equations, they'll try to solve those equations, and they'll come up and they'll say, I've been working on this problem for hours and my equations aren't working, help. And one of the first things I ask is, well, what are you looking for in this problem? And they'll say, I don't know. They don't know what they're trying to solve for or what their goal is in the problem. They wouldn't be able to write out those sentences, And if you don't know what you're looking for, writing, what are your equations for yet? Does that make sense? People often try to jump to those things too fast. And if you can write a good, this is what my answer is going to look like, it's surprising how much of a goal that gives you in what you're writing and what you're looking at. Fair? Happens a lot with variables too. Each one of these is essentially a variable. So we've identified, one, how many variables we need and what those variables stand for. Those variables stand for leaders of that solution, leaders of that solution, and leaders of that solution. Never write an equation with a variable in it if you do not know what that variable stands for. That might sound obvious, but again, I can't tell you how many students I've talked to who write these big equations for word problems that they've been doing for hours. They don't know why their answer isn't working. And I ask, well, what does this X stand for? And they'll say birds. Well, what about birds? Is it the number of birds? Is it the weight of the birds? Is it the speed of the birds? Is it the birth rate of the birds? What about the birds? It turns out it's like weight in one part of the problem and its speed in another part of the problem, because their variable was just bird. Does that make sense? So anytime you're working on big word problems, being absolutely sure you know what your variables stand for and what you're looking for in what terms is a really, really, really helpful start. Cool. Now, the very fact that we have 3 variables here means we're going to need 3 equations. So we're going to have our first equation, our second equation, and our third equation. That means in our problem, we will be looking for 3 relationships, because each relationship should make an equation. Fair? And again, having those goals helps a lot in getting towards how we're supposed to work these out. Okay, so let's look at the problem. Chemist has 3 different acid solutions. The first acid solution contains 20% acid, the second 30% acid, and the third 70% acid. So that's our setup. We haven't been told any relationships yet, right? That's what our parts are. He wants to use all 3 solutions to obtain a mixture of 108 liters. So that's one thing that has to happen, right? So our first equation, we need 108 liters. That fact has to become an equation. Containing 40% acid. Okay, so with the end, we need an end concentration of 40%. None of our inputs were exactly 40%, right? So we need 108 liters. It's got to have an end concentration of 40%. And it has to use 2 times as much of the 75% as the 30%. 2 times as much 75% as 30%. Solution. Fair? So those are the 3 facts that we have to make sure are true. Those are the 3 relationships that have to occur. So that's going to build our 3 equations. Happy with that so far? So let's start with the first one. Remembering that each of our variables stand for a number of liters. This is X number of liters, this is Y number of liters, and Z number of liters. If X, Y, and Z are number of liters, what has to be true for us to end up with exactly 108 liters? We know the liters of 20% plus the liters of 30% plus the liters of 75% must be 108. Right? Do we have a symbol that means the liters of 20% solution? That's supposed to be our X, right? Plus the liters of 30%, Y, plus the liters of 75%, Z. Those numbers of liters are supposed to add up to 100. Okay, so that's our first equation. Let's hold on to the second equation for a minute. I want to jump to that third one just because I do. We have 2 times as much 75 as 30. So just for notational convenience, 2 times as much Z as 30% was the Y, right? So 2 times as much Z as Y. These equations are often hard to write because you want to write them in order. People want this to often be 2Z equals Y. Now, do you think that's right or do you think that's wrong?
Wrong.
Why is that?
There should be twice as much Y as Z.
Yeah. If there are 2 times as much Z, then to make them equal, which one do we have to multiply by 2?
Y.
We got to multiply Y by 2. And one of the things that often helps with that is make a scenario. So 2 times as much 75 as 30 means if you've got, say, 10 liters at 75, then you would need how many liters of 30%? Well, if there's twice as much of this as this, then you'd only have 5 of Y, right? 10 liters of Z and 5 liters of Y would make 2 times as much, twice as much Z as Y. So to make them equal, yeah, that Z has to equal 2Y. So just be careful about that. Fair? Okay. So that's one equation. That's a second equation. Third equation, we need an N concentration of 40%. Of 40%, what? 40% acid, right? 40% acid. So this is all talking about how much acid we have, right? So the amount of acid from the 30%, oh, sorry, from the 20%, I'm just going to say from X, plus the amount of acid from Y plus the amount of acid from Z has to equal the amount of acid from the total, right? The amount of acid in, I'm just going to say it that way, the total. Fair? So the other two equations were liters plus liters plus liters equals liters of just solution. The third equation was these liters equal those liters. These are different. These are an amount of acid plus an amount of acid plus an amount of acid equals an amount of acid, specifically, right? From X, how much of it is acid?
20%.
20% of the number of liters, right? Important thing about percentages, they have to act on something. It's 20% of that many liters. Fair? Plus 30% of the number of liters in Y, plus finish off that equation. This is usually the one that gets people. Hope I'm going to pick on you today. Hope, what'd you write?
I wrote 0.2x plus 0.3y plus 0.75z equals 0.4. Okay.
Why not?
Because it doesn't have, it just has the percentage of acid, not the amount of solution.
Well, you said it very nicely. You said percentage of, right?
Mm.
This was percentage of plus percentage of plus percentage of should equal percentage of,
Okay.
right?
Yeah.
Percentage of what?
Of the, what is it? The 108?
The 108 total. Fair? But I cannot tell you how often that is just 0.4. Part of it is people don't like using that 108 twice, I think. But yeah, keep that in mind anytime you're talking about percentages. They've got to be acting on something. And the units in your problem have to be the same. This is an amount of acid. This is an amount of acid. This is an amount of acid. This has to be an amount of acid. How much acid is there? There's 40% of the 108 liters. Fair? But that gives us 3 equations. The first equation is in its nice form. X plus Y plus Z equals 108. That's nice. It's hard to argue with that. The other one's a little annoying. I might be tempted to turn that into 20x plus 30y plus 75z equals, was that 432? So it's that would be 4,320. 4,320. Just because I don't like decimals. If you're like, no, I like decimals, then fine, go with the decimals. I just multiplied everything by 100, right, to get rid of all those decimals. And then the other one, to put it in this form, it might be nice. That would be negative 2y plus z equals 0. If you want them all in that kind of x, y, z constant notation. But you wouldn't have to do that. You could just use those three if you wanted to. Or you could think of it as that if you want to. It's up to you. But yeah, once you have those three equations, it just becomes like the other problems in this section. Do you guys want to take a minute and solve that one out, or? Yeah, you do. I can see you're already doing it. So I'll give you a couple minutes to do that. I do feel compelled to say, though, I did tell you when doing these, we tend not to use substitution, because usually substitution makes things kind of big and icky. But hopefully you can see this one, particularly in this form, it's just asking to be substituted, isn't it? You're getting x plus y plus 2y equals 108, and 20x plus 30y plus 75z. Oops, 75z. Well, that z is 2y. So times 2y equals 4,320. But that's just too nice to pass up. You know? And I think that's nice in some ways, you know. If the substitution just wants to be this polite, take advantage of it. You know? Here's a nice x plus 3y equals 108. And 20x plus 180y equals 4,320. And then you could use elimination method from that point. You could continue with substitution from that point. Whatever seems most reasonable. I think it is nice to remind you guys that we can mix these techniques if we want. 103/6, is that right? No, 'cause that's a 1. Again, you could have taken different paths through that. One of the nice things about solving these systems is, if you pick a different way through it, that way through it should work. It is nice to go through, either the nicest path or one of the nicer paths through a problem, but what that nicest path is isn't always clear. You get better at making those better choices the more practice you get. But you only learn that by, going down bad paths sometimes and going, I'm not going to do that again. If I see that kind of thing again, I'm going to try a different direction. Are you guys finding those same values? Yeah, okay. I think one of the things, before I let you go, I'll give you another little spiel here. I think one of the things that makes these 9-3 problems difficult is kind of an expectation that's often built up by the time you get to about here in your math courses, that when we're given a big problem, or particularly a big word problem, we should be able to come up with an equation, and that equation should be something that we can just solve in one way or another. And both in chapter 5, we're talking about the exponential modeling questions, where we had to kind of do the problem in multiple steps, in multiple stages. Or here, where we've got to come up with a series of equations. And then to solve that series of equations, we've got to go through a couple of different kind of individual processes that we then bring together. That's very common in the type of problem solving you're going to need to do in some of your finance courses or your science courses, or your chemistry, your physics, certainly your math as you go on. But oftentimes we don't want that to be the case. We look at a problem and we go, okay, I should be able to make this into one big equation. And theoretically, you could. There is one equation that you could write that would model all of this together, and we could build that by then, we almost did. You do this substitution, you solve this for X, and then substitute that X back in to here, and you'd have a big giant equation with only X's in it that you'd be able to solve. But who's going to build that equation all at once? And that expectation of, I should be able to shove all of this into one giant equation all at once, that expectation is a dangerous one. Because even when it's possible, it's usually harder. Fair? So starting to think of your problem solving as, okay, how do I break this into little pieces? How do I build each of those little pieces so I can put that together and then go through my mechanics to build the little pieces I need to solve the problem I actually want. That's how most large scale problem solving works. It just can take a while to get used to because you've done so much where there is one relationship and one process to do. Fair? So keep that in mind as you're doing these. Yes, these are interesting, cool types of problems, but a lot of what you're trying to get used to in this particular section is just this way of thinking through problems in terms of these pieces as opposed to a whole. Fair? Okay. Anything I can do for you before I send you off today?
So I forgot about the test and like what we had determined.
Didn't we say we were going to put it all into one final?
I think so, yeah.
Yeah.
But I wasn't sure just because my open math was still showing on mine at least that there's a test today, and I thought that
Yeah,
was
it shows it on mine too.
But we said no, right?
right.
That doesn't help us not freak out, Matt. All right, I'll buy that. I'll buy that. But it's fun to leave them on and kind of watch you guys stress out.
I don't think it's fun.
For me, it's fun.
We'll get a better hobby.
Well, I have so many hobbies, it's not even funny. Torturing students is just one of the perks. So I'm just going to list all of those on that last day and then combine them into a final sometime this weekend. But that way it won't stress anybody out as much.
Thank you.
Sure. So yeah, that has it all listed at the final. And your 9192 are due Friday? Yeah, okay. Yeah, so if stuff comes up on that 9-3, let me know. But it really is just mostly staying organized and making sure you're working in those pieces.
And will you be uploading this lecture pretty quick?
Yes.
Okay, awesome. Thank you.
No problem. Anything else I can do for you guys? Okay. Then I'll see you later.
Have a good one.
Thank
Have a
you.
good
I will. Thank you too. You too.